We'll now look at Durbin-Watson H test. So if you recall, one of the assumptions of the Durbin-Watson test statistic was that the explanatory variable is non-stochastic. Uh, so what happens, let's say if a regression also includes a lagged dependent variable. So far all the regressions that we have seen look something like this. Beta 1 plus beta 2, x2 plus beta 3, x3, and so on, and the disturbance term. So what happens, let's say if we include a lag dependent variable. So what basically is a lag dependent variable? So let's say that this is how I'm defining my dependent variable here. So say it is assuming values of say 10, here 20, and say uh, minus 10, and then there is, let's say, 35. So when I say lag dependent variable, all I'm saying is that I'm going to regress my yt, let's call this yt, on yt minus 1. So basically what will be my yt minus 1? So when I'm looking at 20, if I'm regressing, let's say, yt on yt minus 1, all I'm saying is the value of yt which was in the previous period. So in this, corresponding to 10, it will be nothing because there was no value before 10, and before 20 it was 10, in front of minus 10 will be 20, and minus 10 here. Okay, so basically when I say lag dependent variable, all I'm saying is the value of y one period before that observation. So sometimes regressions might also include this lag dependent variable. So the specification, if you include the lag dependent variable, will look something like this. Yt is equal to beta 2, let's say x2t, and plus, let's say, beta 3 yt minus 1. So in such a case, again, we cannot apply the usual Durbin-Watson test statistic, and what we resort to is a Durbin-Watson H test. Okay, and the reason is that why we can't apply the usual Durbin-Watson test is because the d value, okay, then the Durbin-Watson test d value might be close to 0, and we might under reject H naught. So we can see this decision rule table, and we can see that if the if the value of d is close to 2, in such a scenario, what we end up doing is we do not reject the null hypothesis. Okay, so if we include a lag dependent variable, that is yt minus 1 in the model, then we can use Durbin-Watson H statistic, and it is defined as given here. H is equal to rho hat, that is the autocorrelation coefficient. So if you recall, this is what we had, this is how we had defined the disturbance term. We said that ut is equal to ut rho times ut minus 1 plus vt. Okay, and since we never observe this true disturbance term, we observe the residuals, the estimated residuals. It becomes something like this, plus vt, or if you want to use some other notation instead of vt over here, maybe some, let's say, vt hat. Okay, so basically we estimate this autocorrelation coefficient, um, and we plug that value here. N is a number of observations. This thing s yt minus 1 square, so remember that we are including a lag dependent variable, so it is basically the variance of this parameter. Okay, so s square yt minus 1 is the variance of coefficient of lagged dependent variable. So we basically calculate the H statistic, and this statistic will follow a standard normal distribution with mean 0 and variance 1. Okay, so let us now define the null hypothesis. Usually this is the first step, but we are doing it in the end because I wanted to bring the context behind this H statistic. So the null hypothesis is that rho is equal to 0, that is the errors are not correlated, while the alternate is that errors are indeed correlated, and if uh, H is greater than the H critical, then we reject the null hypothesis. That's it.